My friends and I spent an entire semester creating 3 AI-based projects. They include a Sokoban level solver, a Filipino-English word classifier, and a bot that uses reinforcement learning to catch digital cats. In this video, I'll share some highlights and key development decisions in the project's development cycle. One of the first projects we built was a Sokoban Solver, or a Sokobot. But what is Sokoban anyways? Sokoban is a puzzle game where players push boxes in a warehouse to get them onto storage locations or goal spaces. A player can only move up, down, left, or right. You can also push a box by moving behind one. It should be noted that only one box can be moved at a time. The game ends when the player manages to occupy all the storage locations with these crates. So how does our bot work? We represented the positions of the crates and the player as a unique state that we had to evaluate. We used greedy best first search as our main algorithm. GBFS works by selecting the most optimal move per turn. For our case, we just select the action that would result in the least total amount of distance between the boxes and their goals per state. Due to the game's mechanic of only allowing push moves for crates, some positions can be made unsolvable. These positions are called deadlock states. We must reduce the number of deadlock states to evaluate to improve the runtime of the program. The deadlock system that we implemented hinges on the fact that valid crate positions can only be reached via valid push moves. In other words, we can simulate pull moves from goal positions and create a map of valid positions. If a crate is outside of this map, we can stop evaluating positions from that state. This is called pruning a position. The Sokoban Wiki is a great resource for understanding the ins and outs of the game. This is where we based a lot of our logic and implementation. Let's see the bot in action. It can easily solve problems involving 6 boxes. The main caveat to our approach is the number of moves to solve isn't optimal. Algorithms such as A* and depth first search with iterative deepening would most likely find more efficient solutions. However, they took a longer time to solve the levels, so we decided to settle on this approach. With a level that has a lot more crates such as this, the search space becomes tremendously big. Our bot would need much more specialized techniques to hope to find a solution, let alone solve it in under 15 seconds. The second project that we did was a word classification model. We had to identify whether a word was Filipino or English from a test set, of course without looking up a dictionary during the program duration. We used a version of decision trees called Random Forest to power our model. Josh Starmer has a great explanation on this technique. In essence, decision trees classify words by creating a flowchart-like structure where internal nodes test features like character presence and word length, which are colored yellow in the diagram, and leaf nodes colored green and blue in the diagram assign the final classification. Therefore, it's critical that you define characteristics or features that are unique to the language. For example, defining common prefixes and suffixes in the Filipino and English language helps the model contrast each word. After training the model, this is its current performance. It hovers around a 93% accuracy on the training and test set that we defined. However, its performance is greatly diminished when testing on English words. More specifically, a recall of 61% means that the current model only correctly identifies an English word 61% of the time. There are only so many features of a word that you can use, and what makes you sure that your new feature is unique to that language? In the field of natural language processing, many researchers use n-grams to overcome this hurdle. Turns out, words of languages have distinguishable patterns within them, and these patterns are captured by counting the number of unique character pairings in a word. With enough data, the frequency of these character pairings become an ID that a classifier model can use to segregate the words. This is how the model performs with the current approach. Can you count the number of correct matches? Write it in the comment section below. As we can see, the model now improves its accuracy to around 97%. Keep in mind that the only feature we used was the character n-grams, and it already outscores the previous feature-based approach. It's also important to try and make the frequency of the Filipino and English words in the dataset about the same to help avoid the model developing a bias. Lastly, we made a cat catcher. You heard that right. We were tasked to catch cats that had random, undisclosed behavior. A player can move up, down, left, right, or do nothing each turn. You catch the cat by ending up in the same location as the cat. How could you even program a bot to do such a task? This is where the power of reinforcement learning shines, specifically Q learning. This problem is based on the Frozen Lake Challenge. Stanford has an online course that explains the theory behind problems like these. In any case, what's important in implementing this bot is to create a reward system that educates the bot if its moves are helping it catch the cat. We decided to give a base reward if the bot catches the cat in its current run. Otherwise, we give penalties to the bot. We also included a penalty for each step the bot takes in the run to minimize the total moves. A distance-based penalty was also awarded to urge the bot to get closer to the cat. These are the training rounds of the cat catcher. We were only permitted to train the bots for 5,000 episodes per cat. An episode is an entire run of the program, regardless of whether the bot has caught the cat or not. Here are clips of the final trained model catching the test cats. Our model makes short work of cats that are deterministic in nature. An example would be a cat that pauses for a turn and then moves a certain distance after. However, our model had inconsistent results when testing against cats that have random movement and cycles. These are the scores for this test cat. The random appearances of negative values indicate that the bot cannot reliably catch the cat. This cat has a 1% chance to automatically teleport to the player position, otherwise it teleports randomly on the board. Our mechanic of actively penalizing distance for each turn is likely detrimental to the bot's performance. In hindsight, we should have programmed the bot such that the distance-based penalties and rewards aren't used, since bot movement is entirely arbitrary. So that's about it. I would like to thank my group mates, Richmond, Chan, and Franz for helping me accomplish these projects. And I would also like to thank our professor for teaching us about these introductory AI topics. If you guys would like to see more CS related projects, remember to hit the like and subscribe. See you guys soon!